Hi, everybody. This is Dr. Niger with the first of our screencasts for the notes on circular motion. Circular motion is going to be a bit of a departure for us. Up to this point, we've been talking about linear motion, so motion in a straight line. We have talked about linear motion that can be horizontal, vertical, or a combination with projectile motion, but it has always been linear in nature. All right, what we're going to talk about in this unit is what happens with motion that doesn't move in a straight line, but instead follows a curved or circular path. All right, so before we can get to the descriptors for that type of motion, we have to talk about two different terms, which are revolution and rotation. Revolution and rotation are different, as we'll see, and they each have their own set of formulas. So when we talk about revolution versus rotation, it's all about an object spinning. So I have a picture of a record player spinning, and then on the outer edge, I have this little bug. All right. When an object spins, it can do so in two different ways. It can turn around an internal axis, or it can move around an external axis. So if it spins, it tends to be moving around something internal, and if it moves in a circular path, we tend to be moving around something external. All right, so let's assume that this record that I have pictured is spinning clockwise. So here's our central axis right here, and we're spinning in this direction around that axis. All right. So we have two objects that are moving in a circular path. We have the record, and then we have the bug out on the edge. All right. So for what is rotation, the easiest way to define that is to decide which of these two objects, the record or the bug, is actually doing the rotating. All right. Well, the record is doing the rotating here. All right. And we know that because rotation requires movement around that central or internal action. So rotation is motion around an internal axis. All right. So another example of something that would rotate would be a figure skater in a spin. Anytime that you spin around, trying to look in a different direction, you're spinning around your internal axis. The Earth spins on an internal axis one time a day, as a matter of fact. So if the record is doing the rotating, then our bug out on the edge must be doing the revolving. So the object that's revolving is the bug. All right. So revolution is a little bit different. Revolution is motion around an external axis. So the bug up here is moving in a circular pattern. They're just moving around the center of that record. So we would say that they are revolving. All right. Again, we could look at the Earth as an example. It does rotate on its own central axis every day, but it also revolves around the sun once a year. So the Earth is a great example of an object that does both of these things. All right, so those are our definitions of revolution and rotation. We are going to focus more on revolution. We are going to be looking at objects moving around an external axis. Rotation is also an important concept in physics, but it has its own set of formulas, and that is just not going to be covered for us in this particular unit. All right, so let's move down to what we have talked about quite a bit, which is linear motion. All right, linear motion, as we know, describes the motion of an object as it moves in a straight line. All right, now we have learned that that straight line can be vertical, so it can move up and down. It could be horizontal, so maybe it moves east to west or north to south, right? Or it can be a combination of the two, such as we saw with projectile motion. All right, so what are some terms that we use to describe this motion? Well, we've used quite a few, but just in general, we talked about the distance the object travels. We talked a little bit about its displacement compared to where it was initially. We've talked about its speed and its velocity. And we also talked quite a bit about its acceleration. All right, so these are all descriptive terms to describe linear motion. Well, circular motion uses these same descriptors. The difference is the object is moving in a circle. All right, so instead of moving in a straight line, we're moving in a circular path. All right. Now, we still use the word linear when we talk about circular motion, which is a little strange, but bear with me. It's going to make sense. All right. When we talked about linear velocity, we know that that linear velocity is equal to the distance covered divided by the time it took to do that. All right. So when we talk about circular velocity, or the object moving in a circle, we're going to find that it's really similar. It's still going to be the distance covered per unit of time. All right. The rotational speed is what we use to describe this speed in a circular path, and it's the same idea. We still use v for it. All right. And again, it is going to be the distance, but around a circle or circular path, and the time needed to go around one time. All right, so basically we want to know the distance around the circle and the time it takes to go around once. All right, now I don't know if you guys remember, but this phrase, time it takes to go around once, is also known as the period for an object that is moving in a circular path. All right, the linear distance that an object moves as it travels in the circle. So I have a circle over to the right. If I were to cut the circle right here and then lay it out flat, then that would be a linear distance. All right, so another name for this distance around the circle is the circumference of that circle. All right, I know this is going to go back to geometry a little bit, but that's okay. We're not going to do too much. All right, so that means we need to know a couple things. We know that the circumference of a circle is equal to 2 times pi times the radius. All right, so if we look at the circle, this piece, this is our circumference. All right, our diameter, right, is all the way across, and then our radius is halfway across. All right, and we remember that the diameter is equal to 2 times the radius. All right, so when I'm talking about the circumference, I need to know the radius of that circle. All right, and that's going to be in meters, and then we multiply by pi, and 2, we still get a unit of meters. All right, so that's going to be the distance around the circle. So if I want to calculate the velocity of a circular motion path, I need the circumference, and then I need to know what the period is, the time it takes to go around once. So the circumference divided by the period is going to get us our speed, our revolution speed. All right, now the unit here is still going to be meters per second, just like we saw with linear motion. All right, so again, velocity or speed is going to be equal to the circumference of the circle divided by time. All right, so let's try a couple practice problems. All right, I've got 2 here we're going to look at. All right, you're riding the Himalaya ride at Six Flags. The radius of the ride is 8 meters, and it takes 5.2 seconds to go around one time. All right, so I've got a radius value of 8 meters and a period of 5.2 seconds. All right, the first question is, what is the frequency? All right, well, remember, frequency is represented by this kind of curvy F, and a frequency is equal to 1 over the period. All right, the period is the number or the amount of time it takes to go around one time. The frequency is the number of passes or the portion of the circle that you can cover every second. So it's a per second unit. All right, so we're going to put 1 over our 5.2 seconds, and we're going to get 0.19 per second. And this per second is also known as a hertz, HC. All right, so the frequency for this particular ride, it covers 0.19 of the circular path every second. All right, so now it wants to know what is our frequency, but in RPMs, which is the same thing as revolutions per minute. All right. A hertz is basically revolutions per second. So there are a couple different ways to do this. I usually take my period and I go ahead and convert that into minutes because for me it's just conceptually easier than trying to convert a hertz into an RPMs. But we worked on this in class a little bit. You can choose what works best for you. So 5.2 seconds is equal to 0.087 minutes. And then the frequency is equal to 1 over that period value. So 1 over 0.087 minutes. And that's going to give us a value of 11.5 RPMs. All right. So every minute we can go around this circle 11 and a half times is basically what we get for our frequency. All right. So now it wants to know how far do you travel going around one time? So if we go around once, that's going to be our circumference, and that's equal to 2 times pi times the radius. So we end up with 2 times pi times 8 meters. And we find that the circumference of this particular circle is 50.3 meters. All right, and remember, that's all the way around. That's not diameter or radius. That's the around portion of our circle. All right, and then last, what is your linear speed? So the velocity is going to be equal to that circumference divided by our period. So 50.3 meters divided by 5.2 seconds is going to be equal to 9.7 meters per second. So that is the velocity at which you are going around this circle if it has a circumference of 50.3 meters and it takes you 5.2 seconds to go around the whole thing. All right, let's slide down to number 2. A turtle has entered the rabbit races hoping to win a blue ribbon. The race course is a circle with a radius of 100 meters, and the turtle covers the course with a speed of 0.15 meters per second. All right, so again, we have a radius of 100 meters, and we have a speed of 0.15 meters per second. All right, so the first question is how far does the turtle travel going around one time? So again, this is going to be our circumference. All right, and our circumference is going to be equal to 2 times pi times our radius, which in this case, we're going to get 2 times pi times 100 meters. All right, so the circumference of this circle is 628.3 meters. So that's the distance all the way around. All right, now it wants to know how many seconds it would take the turtle to go around the course once. All right, and as soon as you see one time around, you know that that is our period, which is our big capital T, and we know that the speed is equal to circumference times that period. All right, so if we plug in our velocity of 0.15 meters per second, our circumference of 628.3 meters, and T for our unknown, cross multiply, do a little bit of algebra, we're going to find the time it takes the turtle to go around the circle one time is 4,188.8 seconds. It's pretty long, actually. Let's see, 4188. Yeah, it takes a long time for that turtle to go around, which makes sense. All right, now it wants to know the frequency. All right, and frequency is equal to 1 over the period in hertz, which means I can keep my seconds. So I'm going to say 1 over 4,188.8 seconds is going to be equal to 0.00024 per seconds or hertz. And that will be the frequency. That's the portion of the circle that the turtle is able to travel every second. So not very much, but he is pretty slow. Okay? So that's just a little bit of an introduction to rotation versus revolution and our formulas for distance around a circle, the circumference, and then the linear speed, which is the circumference divided by the period. Okay, let me know if you have any questions.